so we're going to measure the speed of the CMV. We're going to see what type of motion it is. We've done this a few times with different materials. This time we're going to use what's called a motion detector or a motion sensor. So right now the motion sensor is at the other end of this track. It's actually really nice and neat. Kind of looks like R2-D2. But so it's on and connected wirelessly. All this does is it emits an ultrasonic sound wave that then bounces off of whatever's in front of it. And it will generate motion data at a specific rate. You can change the rate of data collection down here. You can make it up to 200 hertz, so you can increase it or decrease the sample size. So let's try 50 hertz. That means it's going to collect data 50 times per second. So we're going to do that. Actually, let's leave it at 20, just so you can see that first. And what we're going to do is we're going to, I don't want to keep mode, I'm going to put this into continuous mode so that it does it the whole time. And I'm going to do two things here. I am going to make a position versus time graph. I also want you to see what a data table might look like for this, and then we can decide which one is more useful. We can also add columns. You can see this button here will add another column if you want to put the speed in from the sensor. Sorry, I have a whole bunch of other displays open from when I did the photo gates. I can also drop in another type of graph. I can put in a velocity versus time graph. So I'm gonna, we can have a lot of different displays and we can kind of talk about the pros and cons of each one. So what I'm gonna do is I am going to put this on. I'm gonna press record. Or I'm not going to press record. Okay, so let's talk about this. Let's look at the position versus time graph first. I hope you can see that this region here, see that, what I'm highlighting, this part, was before I even put this on the track. What this was reading was the wall. The wall actually it wasn't reading the wall. It was reading this end stop here, this thing, because it's actually exactly 1.2 meters away from the motion detector. So that's what that was reading. And then this was when I put the card down in front of it. It was pretty close, but not that close, about 10 centimeters away that it was reading, okay? And then once it got here, this is where I let it go. So the cool thing with Capstone, especially with graphs, is that you can grab, you can highlight any region of the graph that you want with the highlighter. And once you've highlighted it, if you press this corner button where it says scale axes, it'll show you just that data. So, so that's a really useful tool. And so you can see, so what type of motion does this graph show, right? We don't care about all the messiness in the beginning or even after it crashed at the end. So that's that part. So how do you read this? This velocity versus time graph says it's not moving, right? Because it was reading the end stop. And then this is where my hand got in the way, where I was setting it down, right? And then I was holding it in place. That's this part. And then I set it in, I let it go. So here, this part here is where, and notice that as I highlight stuff, the data table is getting highlighted as well. But you can also scale it by clicking this corner. Probably that's too much here. Sometimes if it blows it up too much, you see too much irregularity. So that's not as useful. So you can shrink it a little bit. But you can see that this is a pretty level graph during this time period. And these times should match. Like if you're doing from 2.6 seconds to 5.2, you should pretty much be able to see the same amount on your velocity time graph. And then on your data table, it shows you the same thing. So you can actually see what position was it at what time, and you can get data about the velocities as well. Okay, shouldn't be any surprise that these values are very close to the values that we got before. So, however, in this case, in this scenario, the data table is really the least useful. And I rarely use it when I'm using a motion detector because look at this position time graph. Using the position time graph, I can say, oh, give me a linear fit for this, and it will, for this part, oops, I can't, I have to select it, sorry. For this, oops, and it'll give me the fit. And as we've learned, the slope of a velocity of a position time graph, the slope of a position time graph is the velocity. So you can also get rid of these uncertainties. It makes it a little cleaner. You can see your R value is like perfect. It's a 1, which is 100% of these points are on the line that you chose. Looking at the velocity time graph, if you put a linear fit on it, what you should see is that the slope is almost 0. And hold on, I want to get rid of the uncertainties, and I want the, yeah, so that's fine. So because it should be just about 0 because the slope of a velocity time graph is acceleration. And if it's moving at constant speed, there is no acceleration. Also, when you have a horizontal line, you should have a really, really bad correlation coefficient. Really, it should be 0 or infinity or error, something like that. So if you got something really bad, that means it's either it's probably a horizontal line. So that's appropriate in this case. So that's how I would analyze these particular graphs.